You may have heard of networks with wide-ranging applications, and they are often growing. For instance, new users join Twitter and follow each other. This adds new vertices and edges to the underlying network over time. Therefore, there has been growing interest in developing dynamic network models. Probabilistic modeling allows us to infer network properties like community structure and predictive distribution. However, the efficacy of probabilistic modeling relies on capturing real-life data properties. For one, most of them are based on parametric models which require prior knowledge of the underlying network. We benefit from non-parametric Bayesian models instead. For another, real-world network sequences tend to be sparse. That is, the number of edges grows subquadratically with the number of vertices. But many non-parametric network models are misspecified. They rely on the assumption of vertex exchangeability that yields dense graph sequences. Recently, an alternative notion of edge exchangeability was introduced for graphs. It turns out by considering edge exchangeability, the graph sequence admits sparsity. We adopt a Bayesian non-parametric model that combines structural elucidation with predictive performance and can grow over time. However, in reality, the edges of a dynamic network might not be observed. What's often known are partial observations of a stochastic cascading process. Senders and followers of recommendations receive discounts on products and they pass to each other. The observations are often in the form of times when different vertices get infected by different contagions. We introduced difference, a generative probabilistic model that is able to identify underlying time-varying network. In each cascade, the first infected time of vertices are observed. Any two vertices that have increasing infection times can introduce an edge. For instance, vertex C could have been infected through A or B. E of C is a set of edges that could have been involved in the transmission. We try to find the most probable diffusion tree in the cascade by calculating the marginal probabilities of all diffusion tree distributions. We sample a set of edges from these distributions and provide them to a Gibbs sampler to update model variables. The probability of an edge is a function of the importance of the cluster in the network, the importance of the source and the destination in the edge cluster, as well as the importance of pair vertices in the network. To sample edge probabilities, we treat each edge as being the last one sampled in the sequence due to edge exchangeability. Finally, the probability of each vertex depends on its edges, modeled by a Dirichlet distribution. Difference is able to track changes of real-world networks and predict most influential users. It can also be applied for diffusion prediction as well as bankruptcy prediction. For more details, please come to our Spotlight presentation or our poster session on Wednesday, the 5th of December.